Okay, thank you everybody for being here today for this periodic seminar. Today we have the talk by Cláudio Maia on the closer look into the Aer model. Aer stands for Acquisition, Execution, and Restitution. Cláudio did this work when he was doing his internship at Thales in France.
2014.
2014, thank you. And he will have around 30 minutes to entertain us on this subject.
Okay, thank you, Patrick. So, good morning, everyone. Thank you for being here, first of all. So, as Patrick was saying, this work is a collaboration with Daniel Garcia Perez from Thales. This work was done in 2014 when I did my internship there. And the objective of the internship in that time was to study parallel models for safety critical systems, which in this case Aer is one of those models. So the context for this presentation is the new commercial off-the-shelf architectures, which we are seeing that lately they are moving from single processors to multi-core processors. Okay, so these architectures are designed considering the average case performance, and the resources are shared within the architecture. So this is an issue when we are dealing with real-time and embedded systems, because functional independent tasks executed in different cores may actually interfere with one another when they are fetching data from main memory. Of course, that when we are dealing with real-time systems, we want determinism. So whenever we have interference due to concurrent accesses, this leads to timing deviations from the worst case execution time that is computed in isolation. So if on one hand we have the parallelism, if with parallelism we expect an increase in performance, on the other hand we have a decrease in systems predictability because we have interference in the platform. So there are several models that try to solve this problem, and Aer is one of them. So in Aer, a task is divided into three distinct phases: the acquisition, execution, and restitution. And the goal of these phases is to basically, so the model works as follows. In the acquisition phase, a task accesses main memory in order to get to fetch data, encode, and store it in the core's local memory. And then in the execution phase, the task will take this data that was loaded into the core's local memory, and it will execute. Then in the restitution phase, the data will be basically stored back into the main memory. Okay. Important aspects about this model are the following. So phases execute non-preemptively, and there cannot be any overlap between memory phases. By memory phase, I mean the acquisition and restitution. So basically, the idea is to achieve temporal and spatial isolation, as we can find it like in standards such as ARIN 653. So to give an example about ARIN 653, here we have a schedule that offers temporal and spatial isolation, and here we see that the schedule is divided into time slots, and in each time slot, only a task within its own partition, in the core, can execute, and we do that for all tasks, achieving thereby the temporal and spatial isolation. Okay. The benefit with the Aer model is that while assuring temporal isolation because phase is executed in time slots, memory phase, okay, we also achieve spatial isolation because we are dividing the execution into these memory phases. So this model has the advantage over the more standard model because it's an interference-free model as a standard one, but in this case, this model offers parallel execution because even though there cannot be overlaps between memory phases, the execution phases can execute in parallel with all other phases in the system. Okay? So the problem with this model so far is the following. There are no schedulability tests for this type of model. There are only constraint programming or ILP solutions which solve specific instances of the problem. And schedulability analysis may seem very simple, but in fact is rather complex because we need to combine multi-cores, the non-preemptive execution of phases, and this leads to interference and blocking, which needs to be considered in this model. So just to give you an example, here we have two distinct tasks, a high priority task and a low priority task, executing in two different cores. Okay, so the high priority task starts executing first. The schedule is low. Starts executing first, and it executes its acquisition phase. Now, at this point, even though the core 2 is idle and can start executing the low priority task, in fact, this model does not allow that. So the task is interfered by high time limits. Okay. Then, at this point, as the high priority task enters an execution phase, then any other task can execute in this time unit. So the acquisition phase of the low priority task in core 2 can start. Okay. Unfortunately, in this case, the execution phase of the high priority task is smaller than the acquisition phase of the low priority task. So here we have a situation where blocking needs to be considered because of the restriction that there cannot be any overlap between memory phases. So this restitution phase cannot start before this A phase actually completes, and so on. Here the bus is a shared resource. Okay, so in this case, actually, we wouldn't get any benefit from having multiple cores because the schedule is pretty much sequential. Okay. Now, to solve this, in this paper we provide a tool that allows us to study the behavior of this type of tasks in multi-core systems, and in this tool, we implemented different priority assignment rules that allows us to schedule these tasks. But instead of the more traditional approaches that use static scheduling, here we have a dynamic scheduling approach. Then we compare these heuristics with a custom global EDF implementation that considers inter-task interference. So to give you, so these are the priority assignment rules. So there are 5 rules, very simple, okay? So the first rule is tasks. So basically the rules only affect the selection of the task when allocating it into a core. So the first rule is based on priority, and this is similar to rate monotonic, where the priority of the task is given to the task that has a shorter period. The minimum acquisition gives priority to the task that has the minimum A phase among all tasks that are ready to execute. The maximum acquisition gives the priority to the task that has the maximum length of A. The minimum restitution is the same as minimum acquisition, but for Rs, and maximum for the same for Rs. So, for instance, take into account, let's say, minimum restitution. Here we give priority to the task that has a minimum R. So in this case, task 3 will be selected first, then task 1, and then task 2. Now, comparing these heuristics with, if we want to compare these heuristics with global EDF, we have to be fair in the sense that, so whenever we have, now I will use whenever I'm talking about the task that will be scheduled using global EDF, I will call it a traditional task, and then we have the AER task, okay? It's easier to understand, for understanding. So, for fairness in comparison in both models, we have AER task, which considers the decoupling of phases, and it has some overhead, and then we have these traditional tasks, which basically execute as a block, and we don't care where the memory requests will occur. So actually, what happens in when the developer is creating the AER task, what happens is that they have like a traditional task, and then they have to include, so they have to decouple the what?
Is it a trick that 8 times 125 is 6?
Man, if I'm not wrong, so it's correct. No?
It's a trick, no? Yeah.
What is this? It's wrong?
It's 2. It's
okay, so it's 0.75. So sorry, I will explain.
Yeah.
So I will explain the reason, but it's okay. You're right. You're right. So here usually what we have is like a traditional task, and then the developer has to actually separate all the memory accesses, and by doing this, at some point they have to include some overhead in the execution. Okay. So for fairness in comparison, whenever we have AER tasks, in this case we have this task with 8 time units, we apply some reduction factor, which basically it is intended to basically convert an AER task into a sequential task, let's say, and applying the reduction factor to remove the overhead of having a traditional task. So basically it's like a conversion overhead. And here the 0 to 25 means that actually in our simulations we use a 25% reduction factor, which actually means that, okay, you are right. So actually this means that the worst case execution time of the task reduced by 25% will give 6, okay? That's nice, but yeah, it's a glitch. Another aspect that we consider when we are dealing with global EDF is that the global EDF, so we are assuming a model that, we are assuming that tasks execute in a COTS platform, and therefore they suffer interference whenever concurrent accesses exist. So as we are modeling it, and EDF does not take into account any kind of interference that may exist, so we apply some artificial slowdown to task execution that is dependent on the number of tasks that execute in parallel. So this is only applied for global EDF. Now I will explain how scheduling works for the heuristics, and then I will, so just to, because global EDF, the scheduling works as in global EDF, so the shorter the deadline, the shorter the absolute deadline, the task, the higher the priority of the task. So here is just to make sure that we are understanding the point. So here in this example we have 3 tasks. So here we are using the priority. So basically task 1 has the highest priority, then we have task 2 and then task 3. We have a ready queue, and then we have 2 cores that are idle. So the next task to execute is selected from the ready queue, and we will select task 1, and we will assign task 1 into the first idle core as long as no other core is executing any other memory phase. Okay, that's the restriction. Then we move on, and then here we are. So this is the acquisition phase. Then we move to the execution phase here, and at this point, as no other core is executing an acquisition phase, the task 2 can start in time unit 2. So the execution continues. Here we show an important aspect of the model, which is the parallelism. Whenever we have E phases, they can execute in parallel with other tasks in the system, even if they are execution phases or memory phases. Okay. Then task 1 completes, and then task 3 can start in core 1, which is the first idle core, and no other core is executing in memory phase. Okay. Now moving on. At this point, we see a situation where some lower priority task is blocking a higher priority task. Here, task 3 is blocking task 2. Okay, and then in the next time unit, task 2 can continue its execution because task 3 already reached its execution. Now, at time unit 10, there is a new release of task 1, but in this case, even though task 1 has a higher priority than any other task in the system, it is not allowed to execute, and that can only happen as soon as the task 3 in core 1 finishes its execution. So basically the rule is whenever a task is assigned into a core, the task should finish its execution before any other task can start. And the reason for this is related to preemption and migration. So basically with AER you assume that you fetch data from main memory, and then you put that data and code into the core's local memory. If at some point you are making some preemption, then you may be replacing data that was previously loaded for the task that was preempted. And if you allow to do that, then you are actually screwing up your model, because then you would have to do all the operation again, which would cause interference in the tasks, and you'd have to actually repeat all of that. So we do not allow that. And then execution continues, and then at this point, as soon as task 2 finishes its execution, then task 1 can start, but this time it will start on core 2 because it's the first idle core that is available and no other memory phase is executing. Okay? Yes,
There's just one clarification.
Yes, sir.
I was not sure. I was not sure that I got it from the beginning. The first and the third phase are exclusive to the entire platform, regardless of the number of cores. And the second phase can execute in parallel.
Yes, exactly. Exactly. So then the schedule executes until the end. Now, in order to basically now we have the heuristics, we have our implementation of EDF. Now we want to actually play with it. So what we do is we generate AER tasks artificially, okay? And then we convert those tasks into EDF tasks according to this rule, which I will explain. And then we measure some data to compare the results. So for the AER tasks, the parameters that we use are, so the phase values are between 1 and 3 times the factor that allows us to enlarge the length of the phases. The period of the task is generated by using a random value between 2 and 4 times the worst case execution time, which is the sum of all the phases, the worst case execution time. Then deadline equals period. For EDF tasks, we convert each AER task into a traditional task. And the reduction that we selected was 25%, just because, okay? It was no, I mean, this is an input parameter, we can play with it, we haven't played in this for you. Concerning slowdown, yes?
And was this transformation because the behavior of the transform system was kind of the same?
So the transformation exists because whenever you have a traditional task and you want to obtain an AER task, you need to actually separate all the memory allocations, all the memory accesses. And if you really want to do that, then you are putting some overhead in this AER task. Because you cannot simply grab a sequential task and then say, okay, now let's use the same values and use it as a AER task. No, you need to actually decouple all the memory accesses from the actual execution, and in most of the cases, and this is where actually the expertise of Daniel is important, because he said, no, you have to, these tasks, they cannot have the same execution time, because when you are doing decoupling, you are putting overhead into the task, because sometimes you need to adjust, you need to actually make the, for the memory requests to work, you need to make certain code, and you need to add certain instructions to the code to make sure that they will execute within those intervals. Because behind this, I'm not talking about that, but then this is like an interval of time that then will have to be submitted to TDMA if you are using a static schedule. I'm not assuming a static schedule, I'm assuming a global schedule. So I'm assuming that, okay, even though I'm not explicitly considering like a TDMA to make the intervals of the exact length, I'm assuming that my schedule takes care of that because of the non-overlapping phases. Okay? So, now for the slowdown value, recall that this value is dependent on the number of tasks that execute in parallel, so it varies. Throughout the execution, if you have 2 tasks executing in parallel, the value will change if you have 3, okay? So just to give you an example, so first I will talk about the list of base slowdown values. So this list was computed, so the values that we use for baseline are this. So this is the value in isolation, okay? This is the value for 2 cores. This is the value for, this is the value if 2 tasks are executing in parallel in the system. This is the value for 3 tasks in parallel, and this is the value for 4 tasks. And we just computed this list for m equals 4. And this list was computed from another paper in which the authors state that they observed a 2.7 times slowdown in a 6-core architecture. Now, if you think that this value is bad, or if you don't have any idea of what are the reference values, I will give you 2 examples. So the first example that you can find is there is one paper where the authors state that for a 4-core architecture, they observed a slowdown of 5.1 times in application execution. And then there's another paper which is more recent from Patrick and Vincent and Miguel, in which they state, if I'm not wrong, that the maximum slowdown that the task can observe is up to 10 times in a 16-core architecture. So here we are talking about half, the slowdown is half of the M cores, okay? So we are kind of conservative in that. We didn't want to exaggerate on that because we are already comparing it with the global EDF. If we say that global EDF is bad when you are considering interference, then people won't accept the paper, okay? So we are assuming like a conservative value. So to give you an example here, assuming that three tasks are executing in parallel in the system, so for each time unit in which they execute in parallel, the slowdown value will actually make them execute like so. If they take 1 time unit, according to this list, they will take 1.35 time units to execute each. Okay. Now, consider the second value. According to so what we did is okay. Assuming that we have a 2.7 slowdown for m equals 6, then we apply the direct proportion to compute these values. Okay. This was what I forgot to mention. Now, for 2 cores. The value should be 0.9, but of course that 0.9 is a speed up and not a slowdown, so we opted to round it to 1. So regarding the outputs of the simulator, the simulator is able to generate a schedule for each of the heuristics, including global EDF. We also have average response times per task set, maximum response times per task set, and a graph with the number of scheduled task sets per heuristic and per utilization value. So these currently are the only outputs that we can get from the simulator. Now that we have everything, we can make the comparisons, and the comparisons that we want to make are the following. So first we want to observe the behavior of each of the heuristics according to phase lengths. Then we want to compare how global EDF behaves versus these heuristics. And finally, we want to see how global EDF is affected by the interference and the number of cores, and when we increase either the number of cores or different slowdown values. So for that, we have other settings. So this is actually the experiments that we did. So we used a 2-core system and 4-core system. We played with different sizes and different lengths of phases. Sorry. And here we are considering, for instance, cases where A's and R's are smaller than E's. We are considering cases where A's are larger than R's because of the minimum and maximum heuristics. We are considering cases where A's and R's are actually larger than the E phase. And we are playing with slowdown values of 1.5 and 2.5 times the values in the list that I showed. Okay. So now the results and the observations. So the first observation that we can make is that when the A and R phases are similar in length, the heuristics that use the minimum and maximum will behave in the same way. So for instance, here we see these are the results in pink and red for the maximums, and for the green and light blue for the minimum. So if the values are the same, the heuristics will behave in the same way. Another important aspect that we can see from the same graph is that when the E phases are smaller than both A and R phases, tasks won't benefit from any parallelism. And we can see that even if the number of cores increase, so here we have an M equals 2, and here it's for 4 cores, we are, so the E is smaller than both A and R, and we see that even if we increase the number of cores, all the heuristics behave back. So basically most of the times what we have is like sequential execution, no parallelism at all. Another observation that we can make concerning the increasing slowdown, we can see that when we increase the slowdown, so this graphic here shows the slowdown for 1.5 and this is 2 times. So when we are increasing the slowdown, we can see that the global DDF, which is the line in dark, in black, actually starts to perform a lot worse. It kind of makes sense because we are increasing the interference that the task is suffering. So of course that when we are increasing these values, the higher will be the interference, and therefore global DDF will behave a lot worse. Now, when we consider 2 cores only, then we see that global EDF behaves. So here we have 2 cores, slowdown 1.5, and then 4 cores, slowdown 1.5. All the parameters remain the same, okay? So here we see that for a 2-core system, global EDF performs a lot better, even when we are applying a slowdown of 1.5 times. But we see that when we increase the number of cores, here we are moving from 2 cores to 4 cores, actually we see that global EDF starts to perform a lot worse, especially in high utilizations. Okay, this is because of the interference. Now, general observations. The first general observation is that we observe that the priority heuristic, which is in blue, actually dominates all the other heuristics in all the settings that we in all the experiments that we did. And we observed as well that the heuristics that use the minimum actually tend to schedule more task sets than the ones that use maximum, and we think that this is because if you allocate always considering the maximum, you are at the same time minimizing the opportunity for parallelism, because you are allocating, I mean, you are occupying the shared resource and the system more, most of the time. So, in conclusion, here in this paper we empirically explored the Aer model because of the lack of schedulability tests. Concerning the observations, we observed that the priority, from all the heuristics that we implemented, priority dominates all the other proposed heuristics. And in some cases, we can schedule task sets that are not scheduled by global EDF. In this case, we are considering our custom implementation of global EDF. Concerning the model, we can state that the model is more viable in some situations than other scheduling approaches that are interference prone. For future work, we want to explore even further the potential of the simulator. We want to generate new metrics. An example of such metric would be like the average allocation per heuristic, and this metric would allow us to basically infer information about how the system is actually allocated most of the times in average. Then, an important aspect that we want to study as well is how the model scales, because as we saw in the when you are using small e's compared to larger R and A phases, then you see that the model doesn't scale. So if you increase the number of cores, then the model will behave more sequential. I mean, will behave sequentially. So here we want to study that scalability for different configurations and different values of n. And with it, I conclude my presentation. So thank you very much.
Now we have time for a few questions.
Yes. Have you considered using ILP formulation to solve the problem?
No, I didn't, because actually this work is based, so the guys from Thales already did that for a constraint programming. So they use constraint programming formulation for the problem, and they already published that. And actually the results of 2.7 times of slowdown were collected using the information from that paper. So that's why we didn't, in that time when 2014, Daniel was trying to convince me to go for this kind of formulation, but then we decided to go this way, and at the same time he decided to, I mean they did that independently.
And did you have some time to see their preliminary results? Because I'm really curious if
I can give you the paper.
implementation scales.
Concerning the ILP and I mean not ILP but constraint programming, I can give you the paper because it's publicly it's public. I mean it was published in some conference, 2015 I guess. That I can give no problem. But the results that I'm using for the list of slowdowns come from that paper. So if you want to observe the amount of slowdown, this is that value, 2.7 times of slowdown for 6 core.
I'm more concerned with the scalability. Of the method.
Okay. With the scalability, I have already some results. And for instance, if you keep the same parameters and if you evolve, if you change m, then depending on the values that you are using, you may observe that the system will behave. If, for instance, in 8 cores, you will see that the system will behave exactly in the same way as 4 cores. And that I already observed. So I kept the same parameters and then I changed just the number of m and then do because here actually this model only benefits if you have larger execution phases. Because if you don't have larger execution phases or execution phases which are larger than both A or R, then you cannot have some parallelism and at some point you will the model won't scale. So this is my experience so far.
So when you speak about constraint programming, what do you mean exactly? You speak about linear programming with constraints, or you speak about constraint programming as a completely independent?
No, constraint programming is completely independent. I guess. I'm not.
Because how to say, constraint programming is not mathematical programming. Yeah, maybe constraint programming comes from artificial intelligence. Yeah? And I think that how to say. It's not surprising that constraint programming is not that efficient, you know. But at the same time, if constraint programming is not efficient, it doesn't mean that mathematical programming is not efficient, you know. Because the thing is, your problem needs to be reasonably simple for like linear programming tools. Even if you have like integer parameters, you can enumerate those integer parameters and the rest you resolve.
No, the model is simple, and actually, even if you consider the constraints that you have, they are very simple. Okay.
Yeah. This is what I understood. Like you do not solve the problem like exactly from the scalability perspective.
I mean myself. No. We are not in this paper. We don't care about schedulability at all. Actually, schedulability. The results were generated. So we generate like several task sets. Okay, and then we measure from those task sets how many of those are schedulable and how many of those are not schedulable. These are measured like empirically. So I generate a schedule and then I check in each time instant if I'm missing some deadline. If I'm missing some deadline, then the task set cannot be schedulable. If I don't miss any deadline, then until the hyper period, then the task set is schedulable.
When you say like you generate those schedules, it means that you enumerate possible execution scenarios.
No, I don't use enumeration. Okay, what I do is using these heuristics. So basically, this heuristic.
But look, if it is an heuristic, then the result is not exact.
Exactly.
So and when you compare, for example, the performance of your second approach, and you make the analysis of the scaling policies, considering that the approach is not exact, the results are
approximate.
But like if you apply an exact algorithm, the performance of different scheduling policies can be completely different. Because imagine your approximate approach, is not in favor of global EDF, but it is in favor of, for example, of global fixed framework. Because the approach is not exact and it is designed in this way. So until you, how to say, either evaluate the pessimism of your approach or you know which favor, how to say, your approach is for.
That's the.
You cannot present such results like saying that global EDF performs worse than something else.
No, what I'm saying is that under these conditions, we observe this. This is what I'm saying. Okay. Now, what you are saying is the next step of the work. Now we are analyzing the schedulability of the model, theoretical schedulability, and then we don't even know if we will have like a sufficient or exact or okay, we don't know yet. We haven't solved that. And then when we reach that point, then the idea is to actually go back and then compare actually how far from the, I mean, once we have the test, then we see where we are with these experiments.
Okay.
That's the goal.
Thanks.
Okay?
Because when I saw global ETF performed so badly.
No, that's what I said. I mean, actually it's performing badly because we are using this modification on global EDF that considers interference. Okay? That's like a modification on the global EDF.
Okay.
And by the way, just to answer that, the heuristics that we use, they just, so it's like a scheduling policy that they select different tasks from the tasks that are ready. I just use the heuristics to, okay, let's select a task which has a shorter period, let's select a task which has the minimum A length. So basically the heuristics is just to decide which task is going to execute next, just to make some variation on the results. Okay.
The last question, because you see what happens. Like also, I also spend a lot of time on those heuristics and stuff. So the difficulty with heuristics is, for example, you generate randomly task sets for like specific settings. And you observe like some result. For example, like that scheduling policy is better or that heuristic is better and whatever. So you change the settings for a task set. For example, you increase the range of task periods, and the results are completely opposite. You know, and so you, for example, you might present all like according to my heuristic, like global PDF performs like so badly, and then you like relax the range of task parameters, and the results are completely opposite.
Exactly.
Global EDF is seems to be an optimal scheduling policy. You know? So
that's the case, and that happens. That's why we.
No,
You mean
nice? Yeah, nice.
Okay. So actually, that's why when you fix the intervals, then we multiply those values by random generated factors to enlarge the data, such that we have more variability on the data.
Yeah, but then you.
But you are right. I mean, but that's a problem when you are using heuristics.
For example, in this particular case, when you multiply task parameters from a value, what happens? You also increase the ratio of maximum task period to minimum task period is more or less the same. Because if you multiply maximum period on a value and minimum period on the same value, the ratio is the same. But this type of ratios are the crucial ones. You know, like the results for Pmax by Pmin, it's sum, like if that ratio is like 1.5, and if that ratio is 1000, the results are completely different.
Okay.
So,
Okay, that's interesting to consider. I mean, that's a problem when we are dealing with data that is generated this way. I mean, everybody that generates data this way has to deal with that, and has to be more especially. It has to be careful to check if the data that they are if the values they are generating are actually covering different sides of the spectrum. That's what's most important. Okay. So, any more questions?
When you were in Thales, do you have a chance to look at the practical applications and the ratio between phases?
So, I don't have those values. However, the values that I will, if you check the paper that I will give you, there they have all that information. I mean, they don't specify exactly the ratio between A's and R's and the length of execution, but from what I know from the experience that I got is that usually these A or R phases you want to be small, you want them to be as small as possible. But I don't know. But in the use case that they use is they have like a flight management system, and they actually have the implementation of it in C and C++, and they use it to measure this kind of data. Okay, but I'm not sure if in that paper they actually provide the values for the lengths. I mean, not the lengths, but the ratio of the phases.
I'd like to put one question regarding the model now.
Okay.
You are considering recurring tasks.
Sorry.
Recurring tasks
Yes.
with periods, but you are considering implicit deadline tasks. Have you thought about extending your model to constraint deadline or unrelated?
I mean, actually, in the results we use implicit deadline in the paper. We consider like constraint deadline, and most probably for the schedulability testing they will be constraint deadline. Okay, but from the simulator point of view, that doesn't make any kind of difference because I just generate the tasks, I have the period and the deadlines, and generate the schedule and then validate if the schedule is a valid schedule or not valid schedule. So what I do is either I check the deadline at the period or I check the deadline at a different point. So from the simulator point of view, it doesn't make any kind of sense. Now, from a theoretical point of view, then that may be actually.
For unrelated deadlines, it would make a difference because if you
I mean, if you are using unrelated deadlines, of course, because you have several task instances at the same time. Okay, but that's a scenario that I'm not considering at the moment. Okay, and I don't even know. Because even in the use case that Alice has, they don't have that situation. Okay, what they have is they have some aperiodic tasks and they have strictly periodic tasks. Okay, that's what I'm saying.
Okay, if no more questions, you can thank the speaker again.